Okay, so in the last video we discussed temperature programming and we were going to move on to carrier gases. So in GCMS, the carrier gas is our mobile phase. Okay, this is a high purity gas that we pump into the system. Okay, and that allows us to move components of our mixture through the column. All right. Uh, Typically, helium is used. Um, More recently, because helium prices have been going up, we use hydrogen gas in certain instruments. Okay. Nitrogen is also used in some of these systems because nitrogen gives better limits of detection with a particular type of detection, which is called flame ionization detection. And we'll talk about that when we talk about detectors. Okay. The speed is a factor. Okay. Right. Speed is a factor. Right. Not only the flow rate of the gas through the column. Okay. Um, but the way that these gases are, the size of these gas molecules changes how fast they can be run with with performance demands. Okay. Uh, Nitrogen, okay, is limited in its range of speeds that it can be used at. Helium and hydrogen, not so much. Okay. Helium is these two, helium and hydrogen, are better for carrier gases. All right, because solutes diffuse more rapidly through these than the larger nitrogen molecules. Okay, and this improves band broadening, right? Because we can recall from the Van Deemter equation that kinetics play a role here. Okay, um, that's pretty much all there is to talk about when it comes to carrier gases. Okay, now guard columns. There are guard columns. Okay, guard columns and retention gaps built into these instruments. Okay, guard columns typically are about 3 to 10 meters of bare capillary. Okay, prior to the analytical column. All right. Some columns have a specially made guard column region that has a slightly different stationary phase, or maybe a higher concentration stationary phase, or it's just a small section of the actual analytical column that's considered sacrificial. Okay, its entire job is to accumulate the stuff that won't pass through the column, so non-volatile substrates, okay, that would otherwise contaminate the column. Right. So you can think of them as essentially um, sacrificial. They are there to prevent stuff that would ruin the analytical column from ruining the analytical column. Okay. Retention gaps, all right, are used pretty much with splitless injection. Okay. And they're meant to improve the peak shape. All right. And they do this by allowing excess solvent to evaporate. All right. Excuse me. All right. And these retention gaps are built at a length of 1 meter per microliter of solvent. Okay. So they are very long relative to the volume that they are meant to disperse. Okay. These lengths are not they're not included in column lengths. That's a really terrible. Okay. So when you buy a 100-meter column, that 100 meters is the length of the actual analytical column. There is a section in front of that is guard column. There is a section in front of the guard column that is retention gap. Sometimes they're separate phases like that. Other times, the guard column and the retention gap are both fused directly to the front of the column, and they're considered the same length of area because a guard column area can also function as a retention gap. Okay? All right. Yeah. So, okay. When it comes to injecting samples, okay, there's two types of injectors. Okay, you have splitless. Okay, sometimes you'll see them called packed, right? And then you have split. Okay. Now, fun fact is that the way most split injection valves are designed, they can function as a splitless injection valve, but packed injection valves cannot function as splits. Okay. So split injection valves are mechanically superior in that sense because they can go both ways. All right. Just a note for you if you're ever considering trying to buy an instrument. Right. With a split injector, okay, uh, or a splitless injector, what we do is we pass through a septum. Okay, we have a heated tube. All right, this is all inside an oven. Okay. So this is a glass tube. Right down at the bottom of this glass tube is going to be some glass wool. Okay. And then this is a septum. Okay. And this is no different than the septa that we use for liquid chromatography, that we use for injection vials in medicine and things like that. It's a self-healing uh, it's a self-healing polymer. So we can use it for multiple injections. Okay. Typically it's made of something like silicone. Okay. We put our needle through that and we inject our sample as a liquid into this tube. Okay. And this tube is heated. All right. The glass wool will collect any liquid droplets and it will allow everything to vaporize. All right. Through this glass tube, we pass our carrier gas. Okay. And the outlet of this injector is the carrier gas plus analyte mixture in the gas phase. Okay. Plus solvent in the gas phase. All right. Excuse me. Now, in a packed injector, that's all it is, right here, just like this. Okay. In a split injector, all right, I'm going to simplify this a little bit. In a split injector, you actually have a two slits. Okay. You have two outlets. All right. One goes to the column. All right. And another, which is separated by a variable diaphragm. Okay. That just goes to waste, right? To external. All right. Actually, if you're clever, you can collect the gas passes out of the split of the injector, and you can then proceed to recondense it and analyze it in another way. Okay. But this is a split injector, and the amount of splitting is controlled not only by this variable diaphragm, but the flow rate of the carrier gas through the system. If you flow a lot of carrier gas through this system, less material is going to make it to the column because the internal pressure in here is going to push everything more towards the external side, assuming that this opening is much wider than this opening here. Okay. Um, if you go back to your analytical books, figure 24-14 in Harris. Okay, that is an excellent image of an injector port. All right. Okay. So, split injections typically are used when the concentration of analyte is greater than 0.1% of the mixture. Okay. Essentially, they allow us to split injection ports allow us to do a dilution without actually having to dilute the sample. Okay. Splitless, okay, the concentration of analyte should be less than 0.1% of the mixture. Right. Quick question for you. What's this in parts per million? What's that in parts per million? Right. So Recall that 0.1% is equivalent to 1 part per thousand, right? And 1 part per thousand is equal to 1,000 ppm. Okay, so we know that if our sample concentration is above 1,000 ppm, we should probably use a split. All right. Okay. The split ratio. All right. The split ratio will tell you the fraction that doesn't reach the injector volume, the column. Whew, I am tripping over my words today. Okay. Okay. So higher split ratios are equivalent to more dilute solutions. Okay. Um, so if you have a solution that is 1,000 ppm, all right, and you pass it through a 1 to 10 split, the column will actually see 100 ppm. Okay, because only 1 out of every 10 parts is actually making it to the column. All right. Now you'll notice that this looks very much like the kind of computation that you would do for an actual dilution. And that's why I said that split injectors allow us to do essentially like an online dilution. Okay. If the analyte is already less than 1,000 ppm, we'll use a splitless injector. All right. Splitless injectors will require, though, that we do something called cold focusing. All right. And cold focusing allows us to improve our peak shape by actually condensing our material back down after it's injected at the head of the column. And that actually reduces any delay of materials evaporating out of the injector oven. Okay? So if there has been some liquid that, needs time to evaporate in here, that will be a leading or a tailing, that would give you a tailing peak. And cold focusing allows us to stop the stuff that was immediately vaporized from advancing to wait for this stuff that had to evaporate, so that we try to keep most of our analyte packed together. Okay? There is one last type of injection. Okay? It is direct injection. I really hope you can't hear the people that just walked by. But if you can, I'm sorry. Okay? These samples are directly injected onto the column, as you might, you know, uh, imagine. All right, there is no injection oven. Okay, a chromatography is initiated. Chromatography is initiated by warming the column. Okay. Now we move on to detectors. So in GCMS, we have several detectors. Okay, we have flame ionization, which is pretty standard. Okay. And in flame ionization detection, we actually burn our eluent, okay? And the signal is going to be proportional to the number of carbons in the sample, okay? So in the molecule, if there's 6 carbons, it'll have a bigger signal than a sample that has 4 carbons, okay? Um, Another kind of common detector is the thermal conductivity detector, okay? And this measures the change in uh, resistance, okay? So we have a resistive heating element that we pass a known voltage through, okay? And Ohm's law states that this resistive element is going to resist the flow of current, and that resistance is going to generate heat. When we pass our sample and the carrier gas over this, okay? Whoa, that was a weird glitch. When we pass the sample plus the carrier gas over that, what's going to happen is the temperature at this resistor is going to go down, all right? Because the thermal conductivity has gone up. There's more material there to take heat away from that resistor than simply the carrier gas alone, all right? Um, if the sample is more thermally conductive, okay? With most carrier gases, though, helium, hydrogen, okay, they're more thermally conductive than typical organic compounds. All right. And so what we actually see is we see that the temperature increases proportional to the concentration of organic material in the carrier gas. Okay. Um, you'll note that in both of these cases, all right, we don't get much in the way of identification information, right? Thermal conductivity, we get nothing. You know, there's nothing there for us to base an ID off of unless we do other experiments like spiking experiments to analyze things by their retention times, right? So with thermal conductivity, ID is dependent on retention time analysis, okay? In flame ionization, you get a little bit more information, but you're still mostly dependent on the retention time. Okay. You can tell, you know, if you know that you're doing, say, a mixture of homologs, right? So say you're analyzing ethanol and then you're analyzing propanol, right? And you're analyzing butanol, right? You can tell the difference between these because butanol will have a much greater signal output than propanol than ethanol, right? Assuming all the peaks are the same shape and all this other, you see where there's a lot of assumptions there, right? But what you can't tell the difference is whether that is isopropanol or is it regular propanol. Is that one butanol or is it two butanol, right? Um, there's an issue there, right? If you're dealing with isomers, good luck, right? And even then, your retention time's not going to help you, okay? And so that's where the most common detector these days comes into play, and that is mass spec. Now, we discussed mass spec already in class, okay? So I'm not going to go over mass spectrometric detection. except to say that the most common methods are the quadrupole. Okay, that's the most common mass filter. Okay, second most common is the triple quad. Okay, and remember that the quadrupole allows us to filter out materials. This allows us to do secondary mass spec on ions, right? So we get tandem mass spec out of a triple quad, right? And then you can get, the magnetic sector and other detectors, based on how much money you're willing to throw at your problems. Okay? As you might imagine, they get more expensive as you go to more complex and more sensitive detection methods. Okay? All right. In the next video, we will talk about HPLC, which operates on all the same principles of chromatography that we've discussed up to this point. However, uh, the mobile phase is a liquid, not a gas. And so we have to deal with the fact that in liquid chromatography, that mobile phase is going to create very high back pressures, whereas in GC, because of the compressibility of the mobile phase, we don't get as high of back pressures. And so there's special instrumental configurations and there's special instrumental concerns that need to be addressed in order to deal with that. Okay? So I will see you in the next video.